Now a cripple wall is just like what you see right here. This is the foundation of the house. This is the wall, that's called a cripple wall, and then this right here is the floor that you walk around on. A good way to find out if you have cripple walls is if you have more than 2 or 3 steps leading into the front door, good chance you have one. Now here's a blown up view of a cripple wall. I'd like to point out this is the floor that you would walk around on. This right here is the cripple wall itself. This is what's called the mud sill, and then this here is the foundation. If the cripple wall collapses, the house will fall off its foundation. Here's a good example of a cripple wall collapse. This is the cripple wall itself. Here is the foundation, and this is the floor of the house right in here. And when it moved this way, the cripple wall was just too weak. And the purpose of a seismic retrofit is to make sure the cripple wall is so strong it does not collapse in an earthquake. Here's a good example of a cripple wall collapse. So this is the floor of the house now. And it used to be that you would go up into the stairs and then into the floor because it was elevated a few feet, and that was the cripple wall. And now the cripple wall has collapsed, and now the floor of the house is way down here on the ground. So the whole purpose of a cripple wall retrofit is to prevent that from happening. Here's a good example of how cripple walls collapse. This is the cripple wall itself. This here is the foundation, and then this here is the floor that you would walk around on. Now right here you can see where the ground has moved underneath the house. And when that happens, inertia causes the cripple wall to lean. And as the earthquake continues, then the inertia causes it to lean even more, and eventually you end up with complete collapse. Plywood is what prevents cripple walls from collapsing. So as you can see here, as the earthquake force tries to cause the cripple wall to collapse, we just put plywood on it to prevent that from happening. Preventing the cripple wall from collapsing is actually pretty simple. Just as we saw, you need to put plywood on it. So as you can see here in this house here, we have plywood on this end, and we put plywood over here. And notice we don't have to put plywood along the entire cripple wall. The engineering calculations behind FEMA P1100s tell us exactly how much plywood we need, and we'll go into that in another video. Now that we have braced the cripple wall with plywood on each end of the cripple wall, when the earthquake force moves underneath the house will try to slide off the foundation. And as the earthquake continues, it'll slide more and more until it falls off. Now, the only way to fix that is to bolt the cripple wall to the foundation. Bolting the house to the foundation is one of the easiest parts of any seismic retrofit. So this is the mud sill right here in pink. And that needs to be bolted directly to the foundation because that's the base of our cripple wall. So we'll come down here and look again. This is the base of the cripple wall. This is the mud sill. Here is the foundation. And when earthquake forces come this way and push on the base of the cripple wall, the mud sill, this is moving right here a couple of inches, so we don't want that to happen. If it moves too far, the house can fall off the foundation. So all we need to do is put in some bolts, connect the mud sill to the foundation, and we are all set. Now that we've braced the cripple wall with plywood and bolted the cripple wall to the foundation, there's one more thing we need to do. We need to make sure that the house stays attached to the top of the cripple wall, otherwise it'll slide off. So let me show you how that works. So here you can see the braced and bolted cripple wall sitting on the house. As the earthquake force comes again and pushes underneath the house as the ground moves, you can see how the house is starting to slide on top of the cripple wall. As it continues to slide underneath the house moves even more. As you can see on the right, it can fall off completely. So what we use is pieces of steel, also called connectors, which you'll see photographs of in a minute. The floor connectors are the last part of our cripple wall retrofit, and let me show you how they work. So this is the floor that you walk on. And then this is the floor framing that supports the floor you walk on. And then this sits on top of the cripple wall. and then this right here is the cripple wall itself. Now, an earthquake comes, we can't have this floor framing slide on top of the cripple wall. Naturally, we'll get damaged like we saw before. So here you can see what happens. Earthquake forces come here, and it slid a little bit. It slid, I don't know, 8 inches or so. We can't have that happen. So what we do is we install these right here called shear transfer ties or floor connectors, and that way when the earthquake force comes this way, that force goes into the top of the cripple wall, and because the cripple wall is braced with plywood and it is bolted to the foundation, it can't move. Here you see 2 floor connectors. This right here is the top of the cripple wall. Now this floor connector here is called a type E connector in the FEMA P1100, and the way this works is this nail and then this nail and then this nail, they nail into this board right here. And there's some other boards, nails that come down this way, and when they come down this way they attach to the top of the cripple wall, and that way when the floor tries to move, it goes into this type E connector, and then that goes into the top of the cripple wall, which is what we want to have happen. Now this works exactly the same way. This is a different part of the floor here. When it tries to move, it goes into this type F connector and into the top of the cripple wall. And now that we've got our cripple wall, you know, if they were covered with plywood and then it was bolted at the bottom, we would then have a complete what's called a shear wall. A shear wall is something that resists earthquakes. It's made out of bolts, it's made out of floor connectors, and it's made out of plywood. Let's review everything we've learned up to now. Here is the mud sill at the base of our cripple wall. Earthquake force comes and tries to push the mud sill off the foundation, and then here we have the bolts to stop that from happening. Now over here we have the full cripple wall. Right here, there's the floor you walk on. And then here's the earthquake force trying to tip the cripple wall over. And then what we've done is we put some plywood on it to prevent that from happening. And finally here we have the floor that we walk on. This is the floor framing. Earthquake force is pushing this way, trying to slide the floor framing off the top of the cripple wall. And then we put in these shear transfer ties, also known as floor connectors. So now we've done everything we need to do to create a shear wall out of our cripple wall, and let's review it one more time. So again, this is the cripple wall. We can't have that collapse, otherwise the house will go with it. And here is our unreinforced cripple wall. So we see right here along the wall itself, it can collapse unless we put plywood on it, and then we come over here and then we see the plywood to keep the cripple wall from collapsing. Now this mud sill right here, we can't have that sliding on top of the foundation, because if it does, the cripple wall will go with it and it'll slide off the foundation. So what we've done over here is we put in the bolts. So we have a bolt here, we have a bolt here, and then there's also some bolts behind the plywood. Now the next thing we have to worry about is the floor can come sliding off the top of the cripple wall. So earthquake forces come this way, slides off the top of the cripple wall, and that's another failure point. And so what we do is we put the steel end right here so that when earthquake forces come this way, they're restrained by these pieces of steel called shear transfer ties or floor connectors. So that's pretty much all you need to do to convert a cripple wall into an earthquake resisting shear wall. This is the reinforcement schedule that contractors use when they're trying to retrofit a house. In this case, we'll take a look at this example. So this one is a 1-story, and here are the requirements. We look at it, it's 1,200 square feet. It's light construction, and basically that means it's got sheetrock and wood siding. In order to retrofit this house, we need to do plywood bracing of 14 feet 8 inches. And then for the mud sill anchorage, that's basically a bolt. So we have a 1/2-inch bolt. We need 7 of those. And then over here for the framing anchors, in this case, these are the Simpson L70s. We need 13 of those. So once all this is done, a contractor can call this fully seismic retrofitted according to Standard Plan A. The reinforcement schedule is based on the connector capacity table that you see right here. Now this table tells us what the capacity is of the various types of hardware that we saw in the reinforcement schedule. So for example, we have the L70 right here. That's a Simpson L70. We see that it can resist 458 pounds, and then it uses this number of nails right here, 8 10-penny nails that are 1.5 inches long. And if, let's say we have an L90 that say we need 10 of them. If we use 10 of them, we can resist 6,000 pounds. Now, this works in such a way that when an engineer does the calculations on a house, let's say he's doing a 1,200 or 1,500 square foot house, and he sees that he needs to resist 6,000 pounds of force, he'll come over here and he'll say, okay, this can resist 600 pounds of force, therefore I need 10 of them. One of the problems with the connector table is that the L70 and L90 values are wrong. So for example, it says the L70 can resist 458 pounds, but if you come down here to the Simpson Strong Tie catalog, it can resist 740 pounds, which is quite a bit more. And the same thing here with the L90. Here it says in the Standard Plan A connector table that it can resist 600 pounds, but in fact, it can resist 925 pounds according to the Simpson Strong Tie catalog. The last frame main anchor we're going to look at is the Simpson H10. Now, in fact, the Simpson H10 no longer exists. It's been replaced by the H10A and the H10AR, which functionally are just the same, and the number of nails. So this H10A, that's for 1.5 inch nominal lumber, and this is for a full 2-inch lumber. So this is a different value from 505 pounds, which is the capacity of the H10 anchor. And if you look at the actual values, it's 565 for the H10A and 490 for the H10AR. So these values are screwed up. The table is based on 505, and the actual values are 565 and 490, depending on what type of lumber you're attaching this to. Now, more importantly, you see here where it says it needs 8 131 by 1.5 inch nails. Well, in fact, it needs 9 148 by 1.5 inch nails into the plate, and 9 148 by 1.5 inch nails into the joist. And so this one is really screwed up. I mean, this is off by, this is, 10 nails off. So this is really, really in bad shape, because if a contractor comes in here and goes, oh, I just have to put in 8 nails, he'll put in 8 nails wherever he wants to put them in, and the value of that hardware will be worth absolutely zero. Simpson will not recognize hardware that is installed with only 8 nails. When it's supposed to have 18 nails, they will not consider it as having any value at all. So right here, we're looking at the capacity of the 1/2 inch bolt. So here the connector capacity table tells it can resist 820 pounds. Now if we come over here, the American Wood Council connection calculator tells us it can resist 1,121 pounds. So that's a pretty big difference between the two. The connector capacity table tells us that the 5/8 bolt can resist 1,170 pounds, whereas the American Wood Council connector calculator tells us it can resist 1,571 pounds, which is a pretty big difference. And this value right here, the 1,571, should have been used in the reinforcement schedule that contractors use. And if it had been, fewer bolts would be required and the retrofits would be much cheaper. This is the UFP10, and these are used, or used to be used, when you didn't have enough room to put in a regular bolt. And they no longer make these, and the value for these are 1,340 pounds. Instead, they make what's called the URFP, and the URFP is similar. In fact, you can install it wherever you can install the old UFP10. However, it has a higher value of 1,530 pounds versus the 1,340. And what that means, if you use this value right here in the reinforcement schedules, you could actually get the same capacity as you did with the old connector capacity table, using less hardware and making the retrofit cheaper. So right here we see two connector capacity tables. The one on the left is from Standard Plan A, And the one on the right here are the values if we use the current building code. So it's pretty obvious, every single one of these is off. The L90 is off. Here it says 600 in the standard plane. The real value is 925. We got 505 for the H10, and then here it is at 565. The bolts are off. Half-inch bolt is 820 over here, 1030 over here, 5/8, 1170 here, 1480 here. 1340 for the UFP, and what's actually used now is 1530. So absolutely every single value in the standard plan A connector table is off, and that really screws up the reinforcement schedule and makes the retrofits much more expensive than they need to be, because as you can see on the right, these values are much higher. In order to reach the engineering goal of the calculations, you can use less hardware using this table rather than the one on the left. Probably the most serious problem with standard plan A is that the shear walls can only resist 190 pounds per linear foot. And this has to do with the nailing. So I'd like to show you that this is from the engineering calculations. And this has to do with the requirements for a one-story light construction house, which needs 14 feet, 8 inches of plywood at 380 pounds per linear foot. And we get the 380 pounds per linear foot by the rated plywood, 1532nd rated plywood, with 8-penny nails, 4 inches on center. So that's what it's supposed to be. Notice here where it says 4 inches edge nailing. Now that does not say staggered nailing. Now one of the first things that any engineer will tell you, if you deviate from the plans, you must talk to the consulting engineer. Now the original standard plan A plans had the edge nailing on the top plate only, but when it was revised later on, it was staggered. So we see here where it's staggered. So we have a nail here, a nail here, a nail here, and a nail here. So we have 4 inches from here to here to here, here to here, and then what that means is we have 8 inches between these nails on the upper top plate. Now let me show you why that's a problem. So if we come over here, and then we're going to have, say, this is an L90 framing anchor. The L90 has nails that go in 1.5 inches. So they go 1.5 inches into the upper top plate. They do not go into the lower top plate. They go into the upper top plate. So when the earthquake force comes, it's the joist is sliding, and when it slides, it's going to go into the nails in the upper top plate only, because that's what it's connected to with the 1.5 inch nails. So virtually, when we have this 1.5 inch, when we have this staggered nailing pattern right here, deviating from the original engineering calculations, which did not allow this, we end up with shear walls that only resist 190 pounds per linear foot. And what that means to resist, to create this equivalent of this, we would have to put in 29 feet, 4 inches of plywood to resist this 5,156 pounds of earthquake force demanded by the engineering calculations. Now that we've seen what plywood and bolts do, we need to figure out a way to connect the two together. Let me show you what our problem is. This is a typical Cripple wall. Now notice that right here, this piece of wood called the mud sill is a full 6 inches going this way. And then these are the 2x4 studs that form the Cripple wall. And those are only 2x4s. So what that does is it leaves a gap between here, the edge of the mud sill, and the 2x4, and that caused a problem. What the problem is when you put the plywood on it, the plywood ends up sitting on top of the mud sill. So you see right here, it's just sitting right on top of the mud sill. It's not connected to the bolts. So we need to make sure that the plywood is connected to the bolts. Now here's one method right here. What's been done here, it's been the mud sill right here has been flush cut with the 2x4s here. So what happened is the contractor came here, cut this right out, and so now we have a notch here. And with that notch, the mud sill is flush with the 2x4s, and then we can simply nail the piece of plywood up right here where you see it. It's nailed straight into the mud sill, and we've connected the plywood to the bolts. These old houses are made of old growth redwood, and so this mud sill right here that we cut, it's also made out of 1,000-year-old old growth redwood. So we cut this notch into it, and then we went and we put our plywood on the cripple wall, and then we nailed it into the old growth redwood. And when we did that, we made a very high quality nail to mud sill connection. And that's why whenever possible, we try to use the flush cut method, since we've been able to attach our nails and our plywood to this very high quality wood right here that you can see is very, very dense redwood. Now compare that to the new growth wood. You can see the old growth redwood is much higher quality than the new wood you would get now. So in every retrofit we do, we always try to use the flush cut method whenever we can. Here's another method by which the plywood is attached to the bolts, and that's with blocks. So you see a block right here between the 2x4s, another block here between the 2x, here and here, and then these bolts go straight through the blocks into the concrete, and you'll see another one right here that goes straight through the blocks into the concrete. And when that's all done, what we do is we take the piece of plywood and we nail it straight into the blocks that you would see behind here. Now remember, these blocks are made out of the very low quality wood. Now the problem with nailed blocks is that they split. Now they don't always split, but they do split. And when they split, it's really a lot of work to try to pull the staples out. So in general, a contractor will just leave it just like it is. Another very similar method is to use staples instead of nails. We still have the blocks, but we just use staples instead. Now that's done to prevent the blocks from splitting. This is a 14-inch long block in between two studs, and it's got about 60 staples in it, and that can resist around 3,800 pounds. Now, if you look at the top, that table is from NER 272, which is a publication from the International Staple Tool and Nail Association, ISANTA. And as you can see, each stale can resist 62 pounds, and that's quite a bit. The last system is the reverse block method, and in this system what we do is we take the piece of plywood and we nail this 2x4 to it from the back. So from this back end we'll nail it just like you see here. The plywood is here, the 2x4 is here, and then there were nails that were put in back this way from the back side. Now we take this full assembly right here, and we take it and we put it on top of the mud sill. So here's our mud sill right here. There's a 2x4. We've nailed that 2x4 to the mud sill itself. Then we've added all the nails that we needed. And then remember, there's a row of nails that comes through the plywood into the back of the 2x4 where you can't see it. This is a very easy to install system and very effective. So as you can see right here, the plywood has been nailed to the back of this 2x4 all the way along. This is a nail gun that's shooting the block into the mud sill, and the mud sill is right here. The foundation is right here. 20 years ago, I was on an International Code Council committee writing a seismic retrofit building code for the San Francisco Bay Area known as Standard Plan A, which is used to this day. And as a committee member, I had access to structural engineers and specialists I would not normally have access to. So I was able to access the lead structural engineer at a research lab at the American Plywood Association, who developed all the standards for the building code. And so this specialist looked at all these different methods and told me which ones he thought were the best ones. So first he said that the flush cut method, the one he would prefer. Second would be the reverse block method. Third would be the stapled blocking method. And fourth would be the nailed blocking method. This is a construction detail from Standard Plan A, and it shows you the blocking system they use. It happens to be the nailed blocking system. So I'll just read this to you slowly. It says, install new 2x blocking between cripple studs, just like we saw, and nail to mud sill with 4 10-penny common nails per block. And then, very importantly, it says pre-drill and stagger all nails to prevent splitting. Now, the authors of Standard Plan A, they knew that splitting was a big problem. They asked the contractor to pre-drill for every single nail. Now, a contractor is not going to do that. They don't have time to do that. They're just going to go in with their nail guns, and sometimes the wood will split and sometimes it won't, and they're just going to keep going. When a block splits and you need to take it out, it's a lot of work. So imagine being in a crawl space that's maybe, I don't know, 2.5 feet, maybe lucky or it's 3 feet. You're crouched over. You got all this safety equipment on you. Then all of a sudden the block splits, and they're really hard to pull out the nails. Do you think you're going to stop and do that? You're not. You're just going to keep going and just leave that split block there and go on to the next job and try to make some money. I don't know how much time most of you have spent underneath houses, but what you see right here in the crawl space is not unusual. I just want to point out some of the things that you see here. So right here, this is some insulation that's fallen down, and the insulation is a problem because if you don't have a respirator, you'll end up breathing in some of this insulation fiber, and it's very, very unhealthy. It can get into your eyes and get into your lungs. So you must always wear safety equipment when you're in a crawl space like this. Right here is some more insulation that fell. Here's some wiring that's strewn around. And then this is interesting right here. This is a hole where the heating duct goes. So this heating duct right here probably starts in the furnace, extends down this way into another crawl space. This foundation was in the center of the house. It goes into another crawl space. And a contractor needs to go into that crawl space because there are lots of foundation walls that need to be retrofitted. So he's going to have to go inside here, drag all his equipment, and go in and get the retrofit done. He's going to have to go underneath that duct in the other crawl space, and he's going to go crawl onto all sides of that foundation and put in his shear walls or whatever he has to do to retrofit this house. Now also, if you look right here, this is where you'd have to crawl on your back. You'd have to crawl underneath here to get to the foundation that's at that location. So you'd have to bring all your equipment and your safety gear and crawl underneath your back and take a look. Now, a building inspector, he's not going to have to crawl around with a bunch of equipment, but he's going to have to crawl into there with a flashlight at a minimum. Same over here. To get into this crawl space, he's going to have a flashlight at a minimum. And that takes quite a while. And not only does it take quite a while, but you have to have a lot of safety equipment with you. You can't just crawl underneath there in your nice clean clothes. And most building inspectors, in fact I would say all building inspectors, they show up in their nice clean clothes. They have 15 inspections to do today, including travel time, including doing all the paperwork. So they just don't have the time to take a look. And you're in every retrofit, standard Plan A or otherwise, you're only as strong as your weakest link. So someone really does need to go in there and take a check and make sure there's not a misconnection somewhere. And unfortunately, you can get your house retrofitted, and then when it's all done, it's not retrofitted at all because someone missed a link and no one checked. And so we can't rely on building departments to do the quality control that is needed. One of the things I discovered while helping teach a class to contractors and homeowners how to use standard Plan A is that they really had a hard time looking at the lines, at these drawings, and trying to figure out what's it look like in the real world. How do they take this and build it? It's very difficult for non-contractors, and even for some contractors who are not used to this kind of work. It's hard for them to conceptualize this. So there are lots of contractors who, they do kitchens normally, or they do bathrooms normally, and then the homeowner will say, hey, here, take standard Plan A, and please retrofit my house. And they may not quite get it, how to do it. So what, really the best thing to do is to take all these details and link them to a video. So for example, we have this one right here, which is for a URFP installation. And so let's say these guys looking at that and wondering, man, how do I install this thing? What does it look like? And all he has to do is click here, and he will go to a video that is made by Simpson Trongthai that shows him the limitations of the URFP. Now note, this does not actually show a contractor how to do something. It gives him general principles and lets him know, the situations where he can use it, which is all valuable information.
The URFP and FRFP retrofit foundation plates from Simpson Strong-Tie are quick and easy solutions for securing your home to its foundation in situations with limited vertical clearance, where floors are supported directly on the foundation or where short cripple walls are present. These plates can accommodate a range of foundation types and perform equally well whether the mud sill is overhanging by ½ inch, flush, set back 1½ inches, 2½ inches, or at any position in between. They are also adjustable up to 20 degrees for angled foundations. The foundation plate you select will depend on the foundation type and sill plate orientation of your structure. For installation of the URFP, here are the tools and hardware you'll need to get the job done. To install the URFP, begin by dry fitting the plate tightly against the mud sill and the face of the foundation. Using a 3/8 inch hex driver and screw gun, install Simpson Strong-Tie SDS heavy-duty connector screws in the far left and far right holes to fix the URFP in place. Install the 3 remaining screws. With a rotary hammer and a ½ inch carbide bit, use the URFP as a guide to drill 2 level anchor holes. Clean out the holes using compressed air. With a 3/4 inch hex driver and impact wrench, install both Simpson Strong-Tie Titan HD heavy-duty anchor screws to complete the installation. Repeat the process for all remaining plates. For spacing requirements, follow your local building code.
But in order to know how to do it, we need to watch a video like this one. The first thing we do is make sure that the lag screws go straight in the center of the mud sill as the manufacturer requires. And we do that with a foundation anchor centering tool, and I'm going to show you how we work with that right now. Now we need to get this lag screw right in the center of the sill, or at least it's got to be a minimum of 3/4 of an inch from this edge and 3/4 of an inch from this edge. Now fortunately in this case we have a sill that is 2 inches thick. So what we've done is we put some holes in this jig such that the hole is exactly 1 inch from the top edge of the sill and exactly 1 inch from the bottom of the sill. So when we put this row of holes here, which are pilot holes to guide the screws, if we put them in exactly at these locations, at the spacings that we have right here, when we put in the URFP, the lag screws will go exactly where they need to go. Now, if someplace on your house, we might find a 1.5 inch thick mud sill, because that's some of the Muir ones are that thick. In that case, we use this upper hole right here, because that's exactly 3/4 of an inch from the top. And if we have an 1.5 inch mud sill, it would be exactly 3/4 of an inch from here. And then once you're all done, your lag screws are right in the center where the manufacturer requires them to be. So now we have a perfectly installed foundation anchor. As you can see here, the screws are straight in the center of the mud sill, exactly where they need to be. So 1 inch from the top, and then we have 1 inch from the bottom. And remember, this is exactly what the manufacturer requires. So this is an example of one that was not done correctly, and I'll show you how it is. So right here is the concrete, that's the foundation. Right here is the bottom edge of the mud sill. Right here is the top edge of the mud sill. It comes straight across this way, and then this is the thickness, which in this case is 2 inches. So you can see this screw right here is right at the bottom, and this one's really close to the bottom, and then this one's really, so none of these screws are going to work like they're supposed to. All the details in Standard Plan A could have something like this, so that a homeowner or a contractor can go and look and see exactly what needs to be done. Don't have to think about it, don't have to scratch your heads, go talk to the building department, try to figure out what these lines mean, because you know, a lot of contractors like remodel kitchens all the time, or do other sorts of things, or just general construction people. And when they're asked by a homeowner to please retrofit their house, they may not be able to understand the plans like they should. So something like this would really make Standard Plan A much more useful. Right here we see a detail for a steel strap that straddles a brake and an upper top plate. Now this is a very important connection, and is often misunderstood by contractors and engineers. And the steel strap here was understood by the authors of Standard Plan A to be of importance. However, I've personally never seen a steel strap on any retrofit I've looked at, and that's over 20 years of doing so. And one of the reasons is people just don't understand why it's so important. The other reason is these steel straps are a big hassle. Not only do you have to carry them around in your truck, but you also have to get a strap nailer, so that's another, $500 or $600 tool just to put in straps. So, practically, no one puts these in, and the main reason is they don't understand how important the brakes and the upper top plate are, and how they can compromise a retrofit. So we have a video link here. So let's go ahead and link to it and see what contractors could have accessible if they would have links in Standard Plan A to help them. So here, let's come on down to the link. We come over here. So there's another very important connection that is almost always, if not always, overlooked in all the retrofits that we look at, and is extremely important, and I'm going to go over that with you right now. Now, a lot of times we don't have a choice about where we're going to put our shear walls. So we come across here on a Cripple wall, and we'll find all kinds of pipes, we'll find gas meters, we'll find sections where the wall was just taken apart, for whatever reason. So we don't have a lot of choice. Sometimes we can put them on the end, sometimes in the middle. We just put them wherever we can possibly get them, and we never know for sure where that's going to be. And there's a problem with that. So the top of a Cripple wall can easily be, 50 feet long, from end to end. So that would be from here to here will be 50 feet. And they don't make boards that are 50 feet long. So what you will find is you'll find a board that's 10 feet long, and then another one that's 12 feet long, and then another one that's, say, 25 feet long. And so all of these, create breaks where they're butted up to each other. So here's an example right here. This is a break in the top plate. So that's the break. So there's a board this way. This is one length of board, and then there's the other board that goes this way. And we'll see right now why that is a problem. So what happens is, let's say we put our shear wall right here at the end of the Cripple wall. So here it is, it's nailed to this top plate right here. And then here's the top plate, and there's a break in it, and then the rest of the house is all sitting on top of this top plate right here. So when the floor goes like this of the house is sitting on top of this top plate, so it's going to also move this top plate this way. Remember, the house moves, the house is attached to the top plate of the Cripple wall, so the top plate moves this way, and when the top plate moves this way, there's a break right here. So the force, that movement, it stops right here. It's not connected over here. So because it's not connected, all the force that's right here, it doesn't have anywhere to go. It just stops right here at the break, and it does not transfer over to our shear wall. So what we do is we've developed a technique by which we can make sure that the earthquake forces do transfer back to the shear wall wherever it might be, and I'm going to show you what that is right now. So all we need to do is we need to put nails on either side of the break and the upper top plate so that we can connect the two together. Now the upper top plate is different from the lower top plate, because the upper top plate right here, and here's the lower top plate, all the entire house sits right on top of this upper top plate. It doesn't sit on the bottom one, it sits on the top one. So that's why it's so critical. So we want to make sure that when the house is moving on top of this upper top plate, that force transfers back over to the other side. And remember, our shear wall is down this way. So all we need to do is we need to put nails on this side, and then we nails on this side. I mean, we can calculate it and figure out exactly how many nails to put in, but man, just nail the heck out of it. You got a nail gun, you just shoot a billion nails on either side and you're all done. So let's see what those nails do to make sure that the entire house is connected to our shear wall. So this right here is the floor that you walk around on, and then this is a floor joist that supports the floor. And you see how this floor joist, there's a nail that comes in here and a nail that comes in here. There's a nail that comes in here, and then there's a nail that comes in here. So when the floor tries to move, it goes into that floor joist and into the nails, see the nails right here, which in turn go to the upper top plate. So the upper top plate is going to move that way as the floor goes this way. When it goes that way, it pulls on these nails right here in the upper top plate. When those nails pull this way, they in turn pull down the lower top plate, because you see how the nails come up from the lower top plate into the upper top plate, lower top plate up there, so they're connected. So the nails pull this way, and when they pull this way, they pull on the lower top plate, and then they pull into these nails again on the lower top plate, which are connected to the nails, connected to the upper top plate right here. So now it pulls on the upper top plate, which then in turn pull against the nails on top of our shear wall, and then all the force goes into our shear wall, which is right where it belongs. So let's go ahead and look at the big picture on that. So here we have the break in the top plate. This entire, cripple wall and floor and everything is disconnected from our shear wall. So now what we've done is we put a whole bunch of nails on this side of the break, a whole bunch of nails on this side of the break. So when the earthquake force comes this way, it travels, through the nails into the lower top plate, because remember, the nails go into the upper and into the lower. So it goes into the nails in the upper top plate. Those in turn are connected to the lower top plate. So then the lower top plate goes this way, comes over to the nails right here. Those nails are connected to the upper top plate right here. So what finally happens is all the force gets pulled on that upper top plate, and this is where all the nails are in the upper top plate. And so all the force is transferred into the shear wall where it belongs. So you see why this connection is so critical. Now, if you don't do this, a large part of your house may not be protected because it's not attached to a shear wall. Remember, a shear wall is designed to attach the floor of the house from the foundation. And if you don't make these connections, joined together like we just looked at, a certain part of the house, might be a big part of the house, will be disconnected from the foundation, and your retrofit will not work as you want it to. In fact, no matter where the break is, if you have 5 of them, 1 of them, how many of them you have, you need to connect all of them together so that all the force goes into the shear walls, which is what you want your retrofit to do. Let's say Seonk had a web page, and on it there were lots of details that someone could look at to help them with standard plan A. So let me show you one that we use fairly often. This is the lag screw detail right here. And instead of trying to look at everything and figure out what it's for and look at all these lines, etc., you can simply go to the video right here. In this video, I'm going to illustrate how lag screws can be used rather than L90s or some other type of frame and anchor in a seismic retrofit. This is a construction detail, and what it shows is a lag screw that comes up here and it penetrates through the lower top plate here, the upper top plate here, and goes directly into the middle of a floor joist. Now this floor joist is always in line with the upper and lower top plates, because this right here on the outside all along here, that's where the siding goes. And in order for the siding to fit, the joist must be right on the edge of the upper top plate and the lower top plate. So when we drive a lag screw through these top plates, and we get it right in the center, which is what's required by the manufacturer of the screw, if we get it right in the center, it has a lot of capacity. It can resist 400 pounds per lag screw, and it allows us to do this when there's sheetrock. So I'd like for you to see this right here. This is sheetrock that runs along here as part of the ceiling. Here's a ceiling joist. And so the ceiling joist can be there, and we can put in one of these lag screws, straight up into the end joist without having to tear out the sheetrock. I'm going to give you a video right now that shows you exactly how we do that. Okay, here I'm standing in front of a shear wall, and I need to make sure that my shear wall is attached to the floor above. So normally I'd have to tear off the sheetrock right up here and then put in a L90 or some type of framing anchor. But in this system, I just use a lag screw. This is from Simpson. It's 6 inches long. And it's 6 inches long for a very good reason. You have to have at least 2 inches of penetration for this to work. So I'm going to show you how these are installed. I had this spacer made at a machine shop. As you can see, there's a hole right through the center of it. It's 7/32 of an inch. And we do that because the screw we use has a pilot hole that's 7/32 of an inch. So let me show you how this is done. Okay, the first thing I do is I put my drill bit through this jig right here, like that. And then I hold it up to the floor joist, to the top plates. And then I drill. Now that is a pilot hole for the lag screw. Now this is exactly 3/4 of an inch from here to here. The floor joist above is 1.5 inches. So when I drive the lag screw through, it'll go right in the center of the floor joist, which is where it belongs. Okay, there's the lag screw right here. Here's my driver. And that can resist 400 pounds for each lag screw. You have to calculate how many you need, but it's a pretty simple affair. And this way we've saved the homeowner all the expense of tearing out the ceiling. It's a whole lot cheaper for the contractor, it's cheaper for the homeowner, and it does a really good job. The big question is, how important is Standard Plan A in terms of public safety? And is it worthwhile to go ahead and make revisions as needed? I'd like to point out that the Association of Bay Area Governments has it on its website for downloading, that the Earthquake Brace and Bolt program, sponsored by the California Earthquake Authority, has spent many millions of dollars on retrofits that use Standard Plan A. I might give it up to 50 million, 60 million, something like that. That the city of Berkeley requires its use when someone wants to use their transfer tax rebate program, which equals 1/3 of the purchase price of a house. And also for the city of El Cerrito has the same thing, where you're required to use it in order to get a grant from the city of El Cerrito. The city of San Leandro teaches classes to homeowners and contractors on its use, so that alone creates quite a few retrofits that use it. And finally, the city of Hayward is starting to require its use for its seismic retrofit. So as you can see, it's a pretty important document, and a lot of money is spent. And plus, there's just the ordinary homeowner who uses it thinking, hey, if I'm going to do a retrofit on my house or hire a contractor to work on my house, I want to get something that is government approved. So as you can see, there's a lot of jurisdictions, a lot of money being spent in the Bay Area for Standard Plan A retrofits.